Hey everyone, in this video, let's do question 1143, longest common subsequence on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we are given two strings, text1 and text2, and we want to return the length of their longest common subsequence. If there is no common subsequence, then we want to return 0. A subsequence of a string is a new string generated from the original one with some characters removed, or possibly none of them removed, without changing the relative order of the remaining characters. What does that mean? So for example, let's say we have the string A, B, C, D, E. Then possible subsequences here can be the entire thing. Maybe it can be A, B, and then we remove the C, so D, E. Maybe it can be A, B, D, E, etc. One thing we can't have is we can't have something like A, B, D, C, because even though this contains characters from this, we have the A, B, the D, but the C is actually before, right? So we can't put it after. So this would be invalid. But that's essentially what it means by definition of a subsequence. So now let's take a look at the examples that we have. Okay, and essentially what we want to do is we're given two texts, right? Text 1 and text 2, and we want to return the longest common subsequence length from it. So you can see here that the longest common subsequence from both of them is ACE. ACE, ACE. So it's length of 3. Here it's exactly ABC because they are both exactly the same text. Here, you can see that there's no common subsequence, and really here, there are no common letters even. So that's another way to understand that there's no common subsequence. Okay, so let's see how we might go about doing this question. Let me go ahead and remove all this, or all of this. Okay? And let's say we have the following. Now, one thing I would do is I would just move this over here just to make this aligned, and you see why I'm doing that in just a second. But let's think about it like this. If we have two texts, then how do we know what can be a common subsequence, right? How do we know what can be common between them? Well, we would have to compare letters, right? We would have to compare the letters of text 1 and the letters of text 2, and we have to do them in such a way such that it preserves order, right? It's not like we can just randomly compare a B with like a A, right? We can't necessarily do that. We need to be systematic about this, and we need to compare them in a way so that it basically follows a specific order. So why don't we maybe start off by comparing the last element? Why don't we compare the last element? Okay, so let's say this is I, and then this is J. This is just one of those things in which when you have like string problems in terms of like finding the common or finding the difference or something like that, string problems, then one of the things you have to do when you have to compare the strings is you start off by comparing one of their letters. And often you compare the last letter and then you work your way inwards. So let's see how this one will actually like play out here. Okay, so I just need you to maybe take this leap of faith that we're going to go ahead and we're going to start comparing these last two letters here. Okay, and why are we comparing them? Because we need to compare letters to understand what is the common subsequence, and we can't just compare random letters. It's not like we can just compare this C here with this C here. Eventually we might arrive at this, but it's not like we can start with this. If we want to start off, we have to start off at the last letter. Okay, so now that we compare the E and the E, they're the same. So what does this mean? What this means that at minimum, the answer would be 1, right? Because at minimum, E and E, this is common, which means it's a common subsequence, which means at minimum, the answer is 1. But this is just between the E and the E, right? We have no idea what is the common subsequence from A, B, C, D and E, A, C. We have no idea what is the common subsequence between these two. And why would we want to maybe find this out? Well, if we can find out the common subsequence between A, B, C, D and also ACE, if we can find this out, then what can we do? Well then, let's assume that we know that ABCD and AC have the common subsequence length of 2, specifically AC here. Now we know that because these two match, because E and E match here, then if we can find the longest common subsequence of these two strings here, well then to that we can just add 1, right? We can just add 1 and then we will get this sequence over here with this extra letter added here. So that's something else we can do. And now how can we maybe translate this into these two pointers that we have? Well, let's say we have E and E matching here. If we have E and E matching here, then we want to look at the rest of the string. So what can we do? Well, we can move our pointers inwards, right? We can move our pointer inwards. So now what are we doing? Now we are looking at D and C. Now, D and C don't match, but it doesn't necessarily mean that there is no common subsequence between the rest of the string, right? Because it's possible maybe there's like a D over here. Maybe there's a D over here, in which case these two match, right? Maybe that's a possibility. Maybe another possibility is that actually there's a C right over here, right? But we simply haven't reached it yet. we can see that there's another common subsequence over here. There's 2 common letters over here. Now, notice how we're still maintaining order, right? Like I'm going from right to left. It's not like I'm going back. It's not like I'm comparing this J with this E over here. That's not what I'm doing, right? So I'm still maintaining some sort of order. Now, what can we do here? We notice that these 2 E's match, so we moved our pointer inward because we want to find the length of the longest common subsequence between ABCD and AC. Now, if ABCD and AC, if their last letters don't match, well, then we can't move both of these pointers inwards, right? Maybe we can eventually, but we can't do that right now because it's possible that C and C match here, and maybe D and D will match over here. So what can we do? Well, we can take like 2 options, right? Either we compare the sequence ABCD with maybe just A, right? Or maybe we compare AC with ABC, right? I'll say that again. So either we compare this entire sequence here with just this letter here, because we know that these 2 don't match, but maybe something from here and something from here match, or we can take this entire sequence here and compare it with this, because we know that D and C don't match, but maybe AC and ABC have some sort of common ground. What does that look like? What we can do is we can look at I and then move J here. We can look at this index. These 2 we can start to compare. Or maybe we can look at something like this. I is here and then J is here. And we actually here we can see, if we were to work our way backwards, we can see that from ABC and AC, we actually have a common ground of 2 here, right? 2 is the length of the longest common subsequence between these. So what can we understand from this? Well, if I go back, if I go over here, and then I figure out, okay, maybe I want to check A and this entire string, or maybe I want to check ABC and then this entire string. Well, the maximum of those 2 is 2, right? The maximum of those 2 is 2, which means that overall, if I'm comparing these 2, if I'm comparing these 2, the maximum is 2, which means, what does it mean? Well, it means that overall, if I go back here, the answer to this was 1 because the E's match plus whatever was returned here, which in this case was 2. So that gives us a subsequence total of 3. And that's exactly the answer that we have. That's exactly the answer that we expect. So let's go ahead and see how we can make this happen in code. Okay, so how might we go about translating this into code? So let's start off where we want to start off, in that we want to compare the last index and basically work our way inwards. So this is clearly a recursive job, right? Because we compare these 2 indices, and then we will go ahead and compare these 2, and then maybe that match, maybe it doesn't, but then we have different ways of going inwards. So let's maybe go ahead and start our recursive call, a recursive function, and see where we can get at. Now, before I do that, I'm actually just going to rename these 2, S1 and S2. And now we need to know a couple of things, right? We need to know what is this last index here. So I would just define that. I would do M is equal to length of S1. I would do N is equal to length of S2. Now when I'm doing my recursive call, what do I need to pass in? Well, I need to pass in S1. I need to pass in S2. And now I need to pass in like this I and J pointer, right? Well, this I and J pointer, initially, it would be M minus 1, right? And N minus 1. That would be the I and J pointers at the start. Okay. So now what do we have? So now we have our helper function, S1, S2, and let me maybe just name this I and J here. Okay. So what is one base case that we have to handle? Well, notice that if I and J don't match, then we'll basically move like one of these pointers inwards, right? And it's possible that at a certain point, either one of these pointers actually goes out of bounds. Maybe we have like a scenario where D is over here, A is over here, and we move J out of bounds. So if we move either I or J out of bounds, what does it mean? Well, it means that we can't form any subsequence, right? Because J is now out of bounds or I is now out of bounds. There's no more string to compare. It's like comparing the string this with a non-empty string, right? There is no comparison here. So we can handle that case. So we can do if I is less than 0 or J is less than 0. This is the case, then what can we do? Well, then we can conclude that there's no common subsequence. Otherwise what? Well, here we started off in which I and J are equivalent. We did S1 at I is equal to S2 at J. If this was the case, then what did we conclude? Well, we concluded that the longest common subsequence is 1 plus whatever the answer of this is and this. So in this case, we moved both I and J inside. What we can do is we can do self.helper, S1, S2, and by moving I and J inside, we basically effectively decrease their index by 1. So that's what we're doing here, and we'll return this. If this isn't the case, then what? Well, if this isn't the case, then either we compare this entire sequence with maybe this, or we compare this entire sequence with maybe this to see if there's a match there. But notice how here we're not adding 1 because we're not certain that we're sure that like these two elements don't match, so we can't really add 1 here. In this case, what we can do is that if the elements are not equal, then we will do return maximum of these two calls. What would the calls be? It'd be self.helper, s1, s2. In the first case, let's assume we keep I as it is, but we move j inside. So that's case number 1. In the second case, what do we do? In the second case, we move I inside and we keep j where it is. So that's what we have. And this is actually the algorithm. So now let's take a look and run our test cases to see if we arrive at the correct answer. And we do. Let's go ahead and submit. And you should see eventually that we arrive at a time limit exceeded error. So this solution is correct, but it just takes too long. Okay, so what is one way in which we can solve this? One way in which we can make recursion faster is by using memoization, right? The way we do memoization is always the same. So I will just paste my memo over here. So we have our memo. Memo is passed in as a dictionary. What do? Well, we need to store whatever is changing in the memo, right? So we need to cache our results, and we cache our results based on whatever is changing. What's changing here is our I and our j. So we will cache these results. So what we can do here is we can do a memo at I and j is equal to this. And then we can just return this. We can just return memo at I and j. Similarly, we will do the same thing here. We will cache this information, and then we will return this. Final thing is we need to check if I and j is even in the memo. If I and j in memo, then we can go ahead and return it. And so this solution here will be effectively much faster than recursion. And it's actually an accepted solution, but you notice it's a little still too slow for us. It's about 1.4 seconds, only better than 20%. So how do we maybe make this even faster? Well, if you have recursion, to make it faster, you make dynamic. You go to memoization, and to make that even faster, you use dynamic programming. Basically, the problem here is that we're still using a lot of stack space because we're still doing recursive calls. Let's see how we can do dynamic programming to basically make this solution a lot better. And we'll still be using this as a guideline, but we actually won't be calling this function here. Okay, so let's take a look at how we can do this. Now, in dynamic programming, what do we have? When dynamic programming, we have an array, right? We have an array. In this case, because we are considering two indices, we actually have to create a 2D array, or basically a matrix, a grid. So I will create my grid here. And what should the size of the grid be? Well, at first glance, it looks like it should just be m by n, right? Because that's what we're storing here, m by n. So at first glance, it just seems like it should be the size of the strings. So let's maybe go ahead and do that. So the way we do that in Python is 0 for in range 0 to n, and then blank in range 0 to m. So what will this do? This will create an m by n matrix. Okay, perfect. So now, before we go into dynamic programming, it's very good and it's actually recommended to understand how we are going to be calculating our answers. Because in dynamic programming, it's not like recursion where you could basically just do your recursive call, and then if you go out of bounds, you just return whatever, and then you come back, right? In dynamic programming, we've got to make sure we don't go outside our matrix. We've got to make sure that if we're looking at I-1, J-1, etc., that information, that answer is already available, and it's not out of bounds in the array. So how can we actually go about solving this? Let's take a look here, and I'm actually going to open my Paint here and show you what I have. Okay, so let me summarize what we have so far. So this is essentially our grid. Our I is basically horizontal, it refers to the rows. Our J is our column, and it refers to our columns. You can see here J-1 is to the left, J+1 is to the right, I-1 is above, I+1 is right here. We're considering an arbitrary cell. Let's consider this cell, I and J here. Now, given I and J, what do we need to know? Well, based on our recursion, it looks like we have a couple of possibilities, right? Given I and J, if S at I, S1 at I is equal to S2 at J, then we want to look at I-1, J-1. If that is not the case, then we want to look at I, J-1, and I-1, J. What this means, what does this mean? This means that given I and J, we have to know these information, these values ahead of time. We have to know these values ahead of time. If we don't know these values, then our answer is effectively going to become wrong, right? And assuming that we know these values, then it allows us to realize like how we actually want to traverse through our grid. It's not always that we can just traverse line by line, row by row. We can't always do that. Sometimes you have to traverse actually in reverse because of the dynamic programming type question. So in this case, I'm at this red square over here, and I need to know these three squares in advance. I need to know I minus 1, j minus 1. I need to know this. I need to know I minus 1, j. I need to know also I and then j minus 1. Okay? So what does this mean? What does this mean? Well, if you think about this, if we are all the way up here, well then I don't actually have access to these three elements up here, right? I actually don't have access to this. I don't have access to this. And I don't have access to this, right? In the case when you don't have access, why don't we just go ahead and we increase our size of our array? So instead of making our array m by n, why don't we make it m plus 1 by n plus 1? So why don't we do something like that? So if we do something like that, what happens? Well, in our case, we do n plus 1, and then we do n plus 1, n plus 1, n plus 1. What happens now? Well, now our array suddenly becomes as the following. So I'll actually move these out of the way. I'll move these up here, and I'll move these to the left. Move these here. So now what does our array become? Now our array becomes the following. This gets increased, and essentially this gets increased, right? You can think of it like this. So now let me just fill in these gaps over here. But now what do we have? Well, now we have an entire matrix in which we have access to all of the values. Now notice what I'm doing. Notice where I'm actually starting, right? Notice where I'm starting. Because this row here, this is actually the 0th row, right? This is the 0th row. This is the 0th column. But I'm actually not starting there because I need access to these three cells here. So what I'm doing is I'm actually starting off at this first cell over here, which is the first row, first column. And then what can I do? Then can I go to the right? Well, I can, right? Because if I go to the right here, well, then I'll have access to this, I'll have access to this, and I'll have access to this. Exactly what we want. And so you notice that by drawing out a grid, we can understand where we can actually go. And then eventually I will solve all of this row. So I'll solve all of this. And then what do I do? Well, do I want to come back here? Well, I don't, right? I don't want to come back here. We already kind of processed this first row and this first column. So then I will come here. And then I will still have access. I'll have access to this, I'll have access to this, and I'll have access to this, which in this case should actually just be filled over here. So I will have access to this information here. So I have access to all of this. So now we can actually traverse the row. We can actually traverse our matrix row by row, and we will have access to everything we need. So what are we going to do here? So one thing we can do is I'll go ahead and loop over my DP array, but notice that when I'm looping over the columns and looping over the rows, we start off at the first index, right? We start off at the first index. So what I would do is I would start off at 1 and then go to, or what would I go to? Well, I need to go to the size of my DP, right? My size of my DP in terms of the rows. Here it goes to m plus 1 rows. So I will do m plus 1. Then J, I will do the same thing, columns, n plus 1 columns. And now what do I need to do? Well, now I basically have what I need right here, and I just need to translate that into dynamic programming code. So what can I do? Well, I need to check that the element here, the current element of S1 is equal to current element of S2. Now, it would be incorrect of me to actually check this, right? It would be incorrect of me to check this. Why? Because we're starting off at index 1. So if you really think about it, we're actually missing the first letter. We're missing the first letter of both of the strings. So here, which is different than recursion, I'm actually going to look at I minus 1 simply because we are offsetted here by 1, right? We wouldn't necessarily like have to offset here. Maybe if we had some intelligent check that says like if we're out of bounds, then make it 0. Then in which case we could just use S at I and then S2 at J. But in this case, it's just often simpler to extend our array so we can have that information. But anyways, here we're checking the last element, and if it is the same, then what can we do? Well, then dp at I and j, this is basically like my memo, is equal to 1 plus dp at what? dp at I minus 1, j minus 1, right? I'm just basically copying what I have here. Otherwise what? Well, otherwise, we have this scenario here. So dp at I and j is equal to the maximum of what? Maximum of dp at I minus 1, j, or let's just copy it exactly how we have dp of I, j minus 1, and dp at I minus 1, j. And that's all we have. Now, once this array is entirely filled, then we'll be all the way down here, right? So what is our answer going to be? Well, our answer is going to be whatever this index is in terms of the rows and in terms of the columns. So this index here is going to be dp at m and then n, right? This will be the last index. And so you can see that's exactly like what we're returning here. We're passing in the last index here. In this term, because we offset it by 1, it'll actually be m and then n. So let's go ahead and run this case. And we can see that it passes. Let's go ahead and submit our code. And we can see that it passes. Perfect. So this is the O of m times n solution. And same thing for the space complexity, because we're storing that in terms of dp. But the main thing about dp we have to understand is we can't just arbitrarily create our grid. We can do that when it's like one directional or like 1D. When it's 2D, we have to often draw this graph to figure out like which cells we need to be filled. And that will actually help us fill out our grid first and then allow us to know where should we loop. Okay, so thanks for watching this question.